yeah, this happened also in a big collaboration with different people from Humboldt University, University of Bonn, Munich, and also Queen Mary. And yeah, we were looking at the gravitational two-body problem, and in particular the unbound case, where we have two black holes flying through space, and at some point we have a scattering event, and then the black holes get deflected, and we have some radiated energy. And the question is, how do we compute classical observables in this system? And yeah, the answer to this question is given in the title of this conference, QCD meets gravity. We can use a lot of methods which were developed for QCD computations and use them for this gravitational setup here. And this was very successful, and a lot of people could compute these observables up to a very high precision. But at some point, you notice that QCD methods are not enough, and we need a third field, and this is algebraic geometry. And yeah, today I want to present this work on 5PM and show how these three fields can work together to compute these gravitational observables. Yeah, so let's start with the gravity. We work in the so-called word-line quantum field theory, where we work in an effective field theory framework, where we model our black holes as point particles and couple these to gravity. So our action has two parts. We have this point particle action, and then additionally this Einstein-Hilbert action. And then what we do is we do a background field expansion, that we look at the trajectories of the black holes and separate the initial trajectory and the deflection z of them. And also we look at the metric and look at the deviation from flat space. These deviations, h and z, we quantize them, and from that we then get these two propagators here. We have, first of all, this word-line propagator, and then additionally this quadratic gravitron propagator. And then then we can then the question is, how do we compute observables? And in particular, we want to compute delta p, the overall change in momentum. And in this theory, we can compute them via one-point functions. To compute delta p, we have to compute the one-point function z here. And now the big advantage of this formalism comes to play, because in the end, we only are interested in the classical part of these observables. And this classical limit is in this theory very easy, because we only have to look at tree-level graphs. So when we look at this one-point function here, we can very easily write down three-point graphs up to a certain order in this post-Minkowskian expansion and compute these observables. And like a special thing about this formalism here is that we always have retarded propagators. So these propagators have a direction, and they are always pointed towards the outgoing line. And by doing this, we can then easily write down an integrand for delta p. And so like we do this via Feynman diagrams. And this was then computed up to fourth post-Minkowskian order. This was first done using scattering amplitudes, and then also done using the word-line effective field theory, and then also this word-line quantum field theory. And so what's missing is this g to the 5 part. So let's look at it. When we look at it and we look at the dependence on the two masses of the black holes, we get this polynomial structure here. And if we look at these outer terms here, these just give us the geodesic motion. So the probe motion of one black hole being much bigger than the other, and the other moving along a geodesic line. So if this is the geodesic motions, these terms here have to give some corrections to that. And indeed, like if we look at this as an expansion in the mass ratio, these terms here give us the correction, the linear correction in the mass ratio. And this term gives us the quadratic correction. And this is then also often referred to as the Self-force expansion. And these terms come with a very different complexity in the integrals. So when we look at the zeros f, this is in principle known to all orders in G. And also when we look at the integrals which appear here, they have like a trivial scale dependence. So it's really not, in principle, it's a numerical problem. We only have planar integrals, and also like the number of master integrals is with 60 at this order quite low. If we now look at 1SF, we still have only planar families, but looking at the number of master integrals, we already see like a big jump in complexity, and we will get very complicated functions, which I will talk more about later. And then additionally at 2SF, we see again a big jump in the number of master integrals, and additionally we also get non-planar integrals. So for now, let's just look at this 1SF contribution. And how do we do these computations? We do this in a very typical loop calculation scheme. We start with some Feynman graphs. Then we have to do some tensor reduction and map all our integrals to our planar family. Then we have a huge list of scalar integrals, I think order of millions. Now we have the big problem in this calculation, the IBP reduction. Here we used a new version of the program Kira, and this is really the technical bottleneck of this computation. I think we used up to 300,000 core hours on a computer cluster. So this is, in principle, this is a simple problem. There's nothing smart involved, but it's just a technical problem. And then once we land on some master integrals, which span the vector space of all appearing integrals, we have to do some differential equation and find a canonical transformation, which will give us full control over the function space and really like reveal what mathematics are hidden in the observable. And once we have done this, we have to compute some boundary integrals and finally get a result for our observable. And yeah, and like for all these parts at this loop order, it's really important to understand the structure of these Feynman integrals and to understand really the mathematical structure which of the physical observable. So let's look at our integrals. Our integral family looks like this. So we have a for loop integral family. And the first thing we notice, we always have these 4 delta functions. And these just come from the fact that at all these vertices on the word line, we don't have momentum conservation, but only energy conservation, which is also the reason why we have at tree-level loop diagrams. And if we picture our integrals as these graphs here, we always draw these delta functions as these dotted lines here. Then additionally, we get 4 word line propagators, which are linear, which we draw as these solid lines here. And then additionally, we get graviton propagators here between the 2 word lines. And altogether, this integral family has 13 propagators and 9 scalar products, so it's really a lot. But the good thing, it's only depending on one scale, which is the relativistic gamma factor or later we also use this x variable. And these integrals have a interesting feature due to the retarded propagators, because they are either purely real or purely imaginary. And this feature tells us actually a lot about the physics they contribute to. Because if we look at our impulse, in our system we have three vectors appearing. We have first of all the impact parameter b and the two velocities. Also we can write our impulse as a sum of these three vectors with some coefficients. If we look at the coefficients coupling to these impact parameters, these terms will give us in the end the scattering angle. If we look at the integrals appearing here, the integrals are purely real and have an even number of linear propagator. And we often refer to this also as even parity of integrals. And here we have mainly conservative effects, but also some dissipative effects appearing. On the other hand, we have these terms coupling to the velocity. And these are giving us, in the end, the radiated energy. And here it's the opposite, that we only have an odd number of linear propagators and an odd parity. And interestingly, here we only have dissipative effects playing a role. And if we would look only at conservative motion, this integral would actually factorize into lower loop orders. And also these two integral families don't talk to each other, so we can really look at them as two separate families with around 230 master integrals. So we can also look at the differential equations of them separately. And here the idea is that we write all our master integrals in a vector and take the derivative of them, and then we do an IVP reduction back such that we get this kind of matrix equation. And we see here like two heat plots of these matrices. And then the idea is not really to solve the differential equations, but to find a transformation in which the dependence of the dimension here factorizes, such that we can easily write down an expansion in epsilon, because in the end we want to take, of course, the limit of 40. And most of these integrals only give rise to logarithmic functions. So everything we see here, which is orange on the diagonal blue, is purely logarithmic, but we see here some purple and red sectors. So let's look at what functions are hidden in there. And let's have a look at 4PM, what appeared there. At 4PM, we had this integral which evaluated at leading order to a square of an elliptic function. And an elliptic function, we can also interpret it geometrically. An elliptic function is just given as a period over an torus. So the question is, can we also assign a geometry to a square of an elliptic function? And for this, we can look at the differential equation of this integral. We have a third order differential equation. And we looked at it, and indeed we can assign a geometry to this function. And in this case, this is a K3 geometry. Now, what is a K3 geometry? In principle, it is just a higher dimensional generalization of a torus. And this third order differential operator has a nice property that it's a symmetric square, such that the solution can be written as a square of an elliptic function. This is nice, but why is this necessary? Why do we need to do this? principle, we don't need to do this for this A3 case, which also appears again at 5 p.m. in multiple sectors. But this is not all we found. We also have this Calabi-Yaus, this integral here, which obeys a fourth order differential equation. And here now it is not really possible to write this as a square of an elliptic function anymore. And the question is, how can we find a canonical form for this integral? And so here we wondered, can we also assign a geometry to this integral? We looked in this paper here. And indeed, we can again ascribe a geometry, which is in this case the Calabi-Yaus threefold, which is again the generalization of the K3. So a K3 is a Calabi-Yaus twofold, and this here is the Calabi-Yaus threefold. And now we can really use the properties of this Calabi-Yaus threefold operator here to find a canonical form via a split into unipotent and semi-simple part, which is given in this paper here, which I won't go into detail. But the reason why we need these properties here is that we need extra functions which appear from certain properties. So here we have this alpha structure function, which depends on multiple solutions of this differential equation. So this omega var pi 0 is one solution of this operator. This var pi 1 is another independent solution. And interestingly, we cannot write it as a symmetric square, but we can still connect it with the same second order operator which appeared in the K3 case, just in this case as a Hadamard product. But now we can really use this feature of the Calabi-Yaus threefold to find a canonical transformation and to find an epsilon form for all these integrals appearing. And then after we do a boundary, after we compute the boundary integrals, we can find a solution for our observables. So let's look at them. The first observable which is interesting is the scattering angle. And in general, at the fifth Post-Minkowskian order, the angle has this structure. So we again see this self-force expansion. So we have the 0SF term. We have at linear order in the mass ratio the 1SF term, second self-force order. And then interestingly at this new cube term, which is also an 1SF effect, but it's given by the recoil, and that's why it appears at the cubed order. And now the interesting question is which functions appear here. So let's look at 4 p.m. again. At 4 p.m. we had the solution given as iterated integrals. In this case it was multiple polylogarithms up to weight 2. So we had 2 times iterated integrals. And additionally, we had these squares of elliptic functions. Now we computed the 5 p.m. terms. And what we saw was surprising. We only saw, again, like these polylogarithms up to weight 3. So we always see like this jump in the weight when we go one order higher. But the elliptics which appeared in our integrals suddenly drop out because they appear in an order epsilon too high. So something is going on there. The same effect was also seen at this 5M calculation in n equals 8 supergravity. And yeah, it is interesting to see to understand what causes this. So we are not sure yet. And the scattering angle then can also be plotted. So we see here the the solutions up to a certain order. So we have here 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m. And here we have the full zeros F solution, and these dots are the numerical relativity data. And what we see is that, so we have the angle as a function of the separation of the two black holes. And we see if we're in the perturbative regime here, we are well in the numerical relativity errors. And if we then go to the non-perturbative regime, if we go get our black holes closer to each other, NR goes up and we don't, here we don't well. So here we really need the resummation from UV. But this is not all we computed. We also have the radiated momentum. But here it's getting interesting because here the integrals with the Calabi-Yaus threefold periods appeared. What is the function space here? Again, we have the multiple polylogarithms up to weight 3. Additionally, we also get now iterated integrals over the square of elliptic, or K3 period, up to weight 3. And we get iterated integrals over the Calabi-Yaus threefold periods up to weight 4. So here we see a weird jump in the weight, which we also don't really fully understand yet. And the question is, can we further simplify these functions? Because if we look at it right now, these parts with only MPLs and K3 periods look really nice compared to, for a for loop result, it looks really nice. And these parts with the Calabi-Yaus threefold period look like a mess. So something is going on. And I think there are further simplifications possible. Yeah, and additionally, we also get these periods and functions coming from the Calabi-Yaus threefold appearing outside of the iterated integrals. Now the question is, how can we evaluate these functions numerically? Because Mathematica doesn't have a function Calabi-Yaus threefold period. So we can evaluate them very efficiently via a PN expansion. We can give as many orders in principle as needed. I think we gave in our ancillary file 500 orders or something. So generating orders there is really no problem. And additionally, we could also do an expansion around the around c, so at around speed of light. So let me summarize. We have completed the 5PM-1SF calculation, including dissipative effects. In this order, it plays a really important role to have full control over the function space. This is the first time in gravitational scattering, but I think also actually in all physical observables in which a Calabi-Yaus threefold appears. So this is exciting. There's some new math appearing in physics. The elliptics drop out, surprisingly, out of the scattering angle, but in the full impulse, we have a really extended function space, and yeah.
Okay, questions? Daniel? Yeah, thanks for the nice talk. Maybe just a naive question about kind of the size of the basis of master integrals. So it was something of order like 242, 246.
Yeah, like, I mean two times, so like, yeah.
But then you also had an explicit example of a differential equation satisfied by one member of that basis, which was fourth order.
So maybe let me
this slide.
Explain this. So in principle, you have these this big matrix, and I mean it's really hard to solve them all at once. So what you do is mean, the reason why you have, I mean, you order these integrals that you have like this block triangular form, and that one, then what you can do is that you first solve the homogeneous equations, which are given on by these diagonal blocks, and then you can also turn these into like a Picard-Fuchs equation, so you turn like 4 coupled differential equations to a 4th order differential equation for one integral.
Is it the case that there's actually kind of smaller subblocks that only talk to themselves that explain what is More questions? Okay, if not, I will abuse my power as chair. This fact that this 4th order differential operator to appear had to do with the simpler second order. Can you make a guess of what's going to show up at higher orders based on this?
I mean, I'm not fully sure. I think the problem is that, for the, I mean, the K3 geometries, they are very well understood, and actually, like always when you have like this one scale problem, you always find this symmetric square for the K3 case. Then, I mean, the Calabi-Yaus threefolds, they're not fully classified, but there's also often that you have this Hadamard product. I have, to be honest, no idea about how you can build this with Calabi-Yaus fourfolds. I guess there should be like a similar structure. Yeah, I mean, I think there is like really a structure, so one should ask like mathematicians on how can you actually build like Calabi-Yaus fourfolds to guess what function should appear, because it really looks like that these geometries are really related to each other.
Thanks. Miguel?
Thanks. Yeah, so yeah, just ask a question because I don't know much about this, but I guess there's going to be tail effects that these are, like now there's going to be plenty more diagrams that contribute to the tail effect. So
Yes.
how much of the information of this, what you showed, can I use for the spiral problem?
I mean, I don't know how to answer this. I mean, there are like more diagrams with the tail effect, but there are also more other diagrams. So I don't know if it.
Yeah, my question is like
percentage-wise, I guess it should stay the same, because I mean the only thing that's now new is that you also have tail effect in the radiated momentum. So there you like lose again some information that the radiated momentum now also has a tail.
I see. Okay.
Hi, sorry if you mentioned and I missed it. What's the outlook for the missing piece? Like on the next slide, you have like, oh, not this one. Yeah, the only missing piece. What's the outlook for that one?
I mean, that's like, for that you have to do the 2SF calculation.
Yeah, what's the status? Like, what is it hard? Is it doable?
Okay, I mean it's really hard. I think it's doable. The question is just, I mean, if we go back to this. So, I mean, here the problem is really just the IVP reduction. The canonical transformation, it's also getting harder. So, like, the integrals are much more complicated. You again have, like, different K3 and Calabi-Yaus threefolds appearing, which are not, I mean, these ones appearing here, they're actually really, really nice. So this gets more difficult, but in principle, we can use the same methods. The question is if you can get through the IVP reduction. I think we can do it, but you never know until you have done it. So, yeah.
Okay, let's thank Benjamin again.